Hello everyone, welcome to our second lecture on rivers. Previously, in our last lecture, we talked about all the reasons why studying rivers is so important in the context of geography. Today we're going to be talking more specifically about different river processes and the different things that make them the shape that they are, and how we can characterize different river features. So I'll bring back this diagram that I showed previously just to remind you guys of the fact that rivers are always in equilibrium, and they want to balance how much sediment they have with how much stream power that they have. So for example, if we have a stream where you have that sediment that's becoming more fine, smaller particles, then that stream can carry more of that sediment away, and you have degradation or erosion of the stream bed that occurs. So you can see that here. As you have maybe a faster stream, for example, then the same process can happen as you have more slope, moving that water faster, and that will in turn cause the degradation to occur, and vice versa with a flattening stream causing more aggradation to occur. And so when you have, for example, a river where you have the sediment size decreasing, then you have more erosion upstream, and eventually that sediment will be deposited downstream, and that erosion upstream and deposition downstream cause the slope in turn to flatten as well, as you take that elevation from the upper regions and move it down. And so it's always a balance of these two processes. And so this movement of sediment can cause rivers to move. You can see here this river that's significantly changing its course over time. And the reason why rivers move and form meanders can be in part explained by this video here, so we'll watch it now.
Compared to the whitewater streams that tumble down mountainsides, the meandering rivers of the plains may seem tame and lazy. But mountain streams are corralled by the steep walled valleys they carve. Their courses are literally set in stone. Out on the open plains, those stony walls give way to soft soil, allowing rivers to shift their banks and set their own ever-changing courses to the sea, courses that almost never run straight. At least not for long, because all it takes to turn a straight stretch of river into a bendy one is a little disturbance and a lot of time. And in nature, there's plenty of both. Say, for example, that a muskrat burrows herself a den in one bank of a stream. Her tunnels make for a cozy home, but they also weaken the bank, which eventually begins to crumble and slump into the stream. Water rushes into the newly formed hollow, sweeping away loose dirt and making the hollow even hollower, which lets the water rush a little faster and sweep away a little more dirt, and so on and so on. As more of the stream's flow is diverted into the deepening hole on one bank and away from the other side of the channel, the flow there weakens and slows. And since slow-moving water can't carry the sand-sized particles that fast-moving water can, the dirt drops to the bottom and builds up to make the water there even shallower and slower, and then keeps accumulating until it becomes new land on the inside bank. Meanwhile, the fast-moving water near the outside bank sweeps out of the curve with enough momentum to carry it across the channel and slam it into the other side, where it starts to carve another curve, and then another, and then another, and then another. The wider the stream, the longer it takes the slingshotting current to reach the other side, and the greater the downstream distance to the next curve. In fact, measurements of meandering streams all over the world reveal a strikingly regular pattern. The length of one S-shaped meander tends to be about 6 times the width of the channel. So little tiny meandering streams tend to look just like miniature versions of their bigger relatives.
Yeah, so rivers are really interesting in the fact that they form these fractal patterns where you have these repeating patterns of meanders as you move downstream that are brought by disturbances along the bed that then get exacerbated by flow. And we see that here where we have meanders that form more and more curvy streams due to erosion on the outside of a bend. So pretty much always you have erosion occurring on the outside of a bend here, and deposition that occurs on the inside of a bend. And the result of that is you have migration of meanders. So the meanders get larger and larger as you have erosion occurring on the outside of the bend, and also those meanders propagate downstream as the river flows in that slingshotting effect that was talked about, move that water in the flow downstream. So you can have these propagations like this. We can think of this a little bit more mathematically when we look at the curvature of the stream. So here we see that these different arrows their length are proportional to the curvature of the stream. So this relatively straight section of the stream has these shorter arrows, and then as you move into this meander bend, these arrows indicate that it's a very curvy area of the stream. And so in order to predict where this stream is going to be migrating, we can use this curvature information. So all we have to do is shift these arrows just a little bit downstream, and we get these red arrows. And so these are just shifted a little bit so that our maximum curvature point here is then shifted down over here. And then this gives us our predicted migration path for the stream. This will be the new location of the stream. And that's because you have that slingshotting effect where the curvature of the stream doesn't really come into play until that water reaches the other side of the stream, and that occurs over a small amount of distance. So we shift these curvature lines just a bit downstream, and we can predict where that meandering is going to occur. And so meandering will occur until the river finds a path that evenly distributes energy along its length. Rivers really like to have fairly consistent slopes. They don't like to kind of gain energy as they move downstream, as you might get when you have a straight channel that'll accelerate as it moves downhill. Instead, it likes to form these meanders and distribute that energy throughout the length. And so we can see where this stream channel is and where the deepest part is by mapping the thowag. So the thowag is the line that indicates the deepest part of the channel. And you can see that here. This line goes through the deepest water all along the stream length. You can see this in cross-section here. This would be the thowag point here because it's the deepest. And generally, you have the fastest flows directly over the thowag. And that's just because you have a lot of friction with the bed, as well as a small amount of friction with the surface. And so you'll have the fastest flows furthest from the banks and over the thowag. And so your maximum velocity isovel, which is the line indicating a constant velocity, will be just below the surface above the thowag. And we can quantify the curviness of a stream with sinuosity. So sinuosity is just a measure of the length of the thowag, the length of the channel, divided by the length of the valley that contains it. So for example, if we have a very curvy stream that's meandering all over the place here, we're going to have a very large length of the thowag relative to a fairly small valley center line, and therefore we'll have a high sinuosity. And that's just a good way of measuring how mature a stream is and how curvy it is. Next, let's talk about oxbows and cutoffs. So not just cows and genes, but in their relation to rivers. So an oxbow lake forms whenever you have a cutoff that forms in the meander. So you can see here that we have two meanders that that hit each other and cut off this section of stream here. And this little patch of land here that gets pinched out is called the neck, or the meander cutoff. And the lake that forms after that cutoff occurs is called an oxbow lake. We also have point bars developed. So on the inside of a bend, you have deposition. So on the outside of the bend, you have erosion occurring and that meander propagation. But on the inside, you have deposition of sand. And this point bar can extend out as you have more deposition occurring. And that very sandy region of the floodplain is called a point bar. Additionally, we can have yazoo streams. So oftentimes a larger stream will have a smaller yazoo stream that runs relatively parallel to it on the terrace above it. And so this yazoo stream is just a small stream that runs relatively parallel to the larger stream. And you can also see here that this meander bend is migrating downstream, just like we talked about. And so you see this meander head moving slowly downstream all the way down to here. So the type of river depends on both the slope and the flow velocity. And we can characterize a stream based off of how much braiding there is and the width relative to the length of the stream. And so when we have relatively low slopes and low flow velocities, we can maintain a fairly straight channel. But as you have increasing flow velocity and increasing slope, you have more energy. And so any of those disturbances start to form meanders, and you have a meandering river. And then as we get into even steeper slopes and higher flow velocities, we can get into anabranching streams, which is multiple stream channels that are kind of interlaced in between each other, and they can cross and form these islands. And then lastly, when we have relatively high slope and high velocity, we have braided or anastomosing streams. And this is when you have a full lace work of streams that are moving in between each other that are trying to accommodate this excess slope and velocity. And so you have an increase in sinuosity up until you have meandering, and then you have a decrease in sinuosity as this entire river takes up a good portion of the valley. So we can think about too what would happen if we had a decrease in grain size. Remember, when we decrease our grain size, then we have more erosion occurring upstream and that sediment being deposited downstream. And so therefore you have a decrease in slope. And so you can think about if you decrease your grain size, you might go from an anabranching stream to a meandering stream. And that relates back to that diagram that we talked about. And in the same manner, we can kind of plot this, this same graph based off of sediment size and sediment load instead of velocity, with anabranching and braided streams having some of the largest sediment loads. Next, let's talk about drainage patterns. So rivers don't flow alone. They drain an entire watershed area, and the pattern in which those drainage networks develop is called a drainage pattern. And we can have four main types. So the most common is a dendritic drainage pattern. And dendritic means tree-like. And you can kind of see that this is kind of shaped like a tree as you flow water off the surface and it gets funneled to a central point. Next, we can have a radial drainage pattern, and that's when you have a large mountain or large ridge that all of the river is flowing away from this point. For example, if you have like Mount Shasta, is a big prominent mountain that doesn't have much topography around it, and you just have water that's flowing out from that center point here. Next, we can have rectangular drainage networks. So oftentimes in limestone, highly fractured and jointed bedrock, you can have these right angles that develop along those joints. And so you, instead of these kind of curvy intersections, you have more right angled intersections. And then lastly, we have trellis drainage networks. And this is when you have a mountain ridge that develops, and you have these linear ridge-like features. Maybe you have a Horst and Graben topography that we talked about previously as well. And so the river doesn't like to cut into those ridges very much. And so you'll have these kind of parallel river systems that then cut through the ridge perpendicular to them at only a single location, and that will be the trellis system. We can see here that this is a radially drainage network from this mountainside, where you have these rivers coming off in all directions with these kind of dendritic rills, these small drainage networks that develop all throughout the ridge line. All right, so let's take a break there, and we can continue on talking about rivers and the geologic and geomorphic features within them when we return. I'll see you guys soon.